Welcome to a tutorial prepared for simulation and prototyping at Lawrence Technological University. This tutorial is going to cover how to develop a series of multiple planar cuts through a solid object. And we'll look at both how to set up that file. We're going to use random numbers to create a set of random planes to be able to prototype. And then we're going to look at a number of visualization options related to this. So to get started, what I want to do is show you where we're heading. And what you can see on the right-hand side in the Rhino window is on the left, a full cube, and then a series of cuts, 5 cuts, planar cuts through that object, and then the resulting form on the right-hand side. Under each one of them, you can see the volume. You can see it decreasing with each step. And then below it, we can see the object that's being removed and the volume of that fragment. And on the far right, all of the fragments put together. So the way that this is set up, I've got 3 random parameters, or 3 parameters that drive some random numbers. The 3 parameters are seed values. The seed value is a number that generates a random number or generates a series of random numbers. And we'll see that in a second. My first random number sets a set of random numbers for the planes and their location in plan or rotation in plan. The second random number or second seed value for the random numbers is the position and their rotation in elevation or in section. And then the last seed value controls the location of the plane in relationship to the form. And so they're kind of going from the seed value with the most impact to potentially the least impact or the least difference in terms of that change. And we can see there's a little bit of, it's a little slow, but you'll see this is a pretty complex file with a lot of multiple things being displayed. But you can see that all of the things being represented in Rhino are all live, and they're all being driven directly from that. And so what we will do now is we'll start with a fresh file, and I want to work with you to build up something similar for yourself. And so let's start doing that. I'm going to start a new Rhino file, large objects feet, and I'll start a new Grasshopper file. And with these, you see, I want to make sure that I draw the full names for you. And we'll set this up. And you've also started to get a sense now too that if you include geometry that's tied to Grasshopper, you need to, if you're going to share the file, you have to share both the Grasshopper file and the Rhino file. So what I want to do with this is to actually build everything. For the most part, as we get into the second part of the tutorial, we might have some things that we work as to locate things. But to start, let's just start with everything in Grasshopper. And what we want to do is start with a point. So I'm going to double click and say construct point. It's going to default to 0, 0, 0 at the axis system. That's okay in this instance. We could put 3 variables or 3 values in for those if we wanted to change it, but we don't need to. We're going to start with our mass, and so our cubic volume. So why don't we look at that? That's going to be a surface primitive, and we can see there's 5 options for boxes. We're going to use center box, just because it's going to give us exactly what we need with kind of minimal input. And we'll set the size for this. So I'm going to choose 1 less than 5 less than 10. And I'm going to use 5 for X, Y, and Z. So this will give us a kind of simple cubic volume here Now that we have that, I can move to perspective view. What we also see is that with the center box, the center point is exactly in the middle. So our box does not sit on the XY plane. It sits halfway above and halfway below the XY plane. But we've got our center box now. And so from here, what I want to do is I want to begin to locate a point in space. And we'll do this by using a really simple object or simple component under points. So that's points are under vector. And the point that we're going to use is point polar. And what point polar will allow us to do is to control a point or locate a point in a rotational XY plane, in a rotational Z plane, and then offset it from another point. And so our base is going to be XY. And we'll just need 3 parameters for this. So for the XY angle, this can be anything from, let's say, 0 less than 40 less than 360. The other thing that we need to remember to do is that these are set to radians. And you can see when you mouse over, angle in radians. If we right click, we can change this to degrees. And that's the way that we're going to be working with these. So I can plug this in for XY. For Z, this will be its kind of altitude or its rotation in plan. So for this, we can say 0 is less than 20 is less than 90. Oh. 0 is less than 10 is less than 90. And so if let's set this offset value. And the offset value for now can roughly be the size of the box. So let's say 1 is less than 4 is less than 8. And we'll see the way that we can change things with that. So that'll be our output. So now it's set to 4. It should be within the box. If we look from above and we change our first value, we'll see that we're going to go from 0. We're going to rotate counterclockwise around and then end up at 360. So that gives us the kind of orientation. This is similar to a sunlight system in a rendering program where you have north and you have the rotation that way, and then the time of day sets the altitude of the sun. So if we look at this from the side, we'll also see that if we go to 0, it's horizontal, and as we go to 90, it's totally vertical. And because this rotates 360, we don't have to go 0 to 180, we only have to go 0 to 90. And then you'll see the last value just projects that out. And it's using the center point as its starting point, and then it's projecting out in all directions. So this is a really simple, really great component to use if you want to start to locate points in relationship to another point in a kind of spherical space. So now that we have that, let's draw a line with 2 points. And these 2 points will be the starting point will be our 0, 0, 0. And our end point is going to be the point that we just made. So now we get a sense for that. Again, keep moving your values to make sure that everything's connected. We can see that that line is connected and that's working. And what we want to do next is to make a plane, because we're going to use a plane. And the way to think about this is that the plane is a kind of icon. It stands in for a kind of flat axis system. And even if the plane is small, the plane is an icon for something that's an infinite plane. And so planes are nice for us because it will intersect our volume. And so if we go up to vector again, there's a number of different ways to set planes. We're going to use plane normal. This is a nice simple one that allows us to set a plane normal to a line. And so we have our line, which we just drew. That will be our z-axis. And we can see now that the plane that's here is perpendicular or normal to the line that we drew. And what we want to do is locate it at the end of that line. And so our origin for our plane is actually going to be our rotated point. And so that gives us our plane at the end of that line. And we can just come back and we can modify. We can see this is rotating it around, as well as rotating it up and down. And then in and out. And we'll see where that intersects. So the next thing we want to do is to basically cut this. And the way that we're going to cut it, and I'll jump ahead and then I'll fill in a gap. The way that we're going to cut it is we're going to go to intersect, and we're going to use solid difference. And solid difference looks for 2 B reps for us. And our second, so we're obviously going to use our center box as our first B rep. And in this case, A is usually what remains, and B is what we're subtracting with. We're not going to use a plane, but there's a good tool here called surface primitive, and it's plane through shape. And so what's nice about that is that we can, let's see, plane. Yeah, so plane through shape gives us the plane, which we already have. And so there's the plane. The shape through which we want to create that, because it needs to know that it's going all the way through. And so you see it just created this green plane. It's green because we have it selected here, and it's going all the way beyond. It has this other input called inflate. Right now 1 works, but let's say we wanted this plane to be much larger to cut through other objects. We could increase that value from 1, and we could increase the size of that plane or that surface. So now that we have a surface, this is a B rep, and so this can be our second B rep here. And now something, you know what, actually I said that before. Let me flip these around and see if this works. Yeah, I think I was right before. So the box is what we want to keep. And so that should go to A. The plane will be B. But the problem that you'll see is that what's left, if we hide our original box now, is that it's only the small fragment that's left. And the reason for that is that sometimes our plane can get flipped. And the way that we can remedy this is there's a component called flip. It allows us to flip the normal of a surface. It's a really simple tool. We just give it a surface, and it gives us a surface that's where the normal is flipped. And so now we see that our box has that piece taken out of it. So I'm going to hide a few things here. We don't necessarily need to see our plane anymore, even our lines or our points anymore. Okay, good. So let's go back to our sliders and just take a look at this. As we rotate the plane around, oh, and I said we didn't need I hid the surface, but not the plane. So there we go. So now we can see we're getting a real-time cut through our box as we rotate the plane around in plan, as we rotate it in section or an elevation, and then also as we move it in and out. And so all of that is working for us. That looks really good. What's nice with this, and other people may have had better experiences, but sometimes in Rhino, when you're working with the surface modeling, the Boolean difference doesn't always work. Sometimes you get Boolean difference failed. I found this in Grasshopper to be pretty robust. And so this is a really simple definition. This now gives us the plane cutting through a cube. And again, the cube could be any type of object that you want it to be. It doesn't have to be a cube. In this case, it is. So we have this. So I want to do a couple more things. First of all, let's come back to these. We have our difference. What I want to do is I want to do more than one plane cutting through this, and I want to randomize them. And so the reason why I like to use random is that we could create 5 planes. We could replicate or duplicate all of this, and we could do it 5 times. So we could use the sliders to locate the plane for it to cut through. And there may be moments where we want to tweak some of those things, but at an early stage, maybe we want to try a large number of these to see what we get, and we want to develop a range. So let's develop this a bit, and I'm going to move all of this maybe over a little bit. And what I want to do is replace these with random numbers and a group of random numbers. So let's find out what random needs when we create it. It needs a range, which means a domain for us. It wants to know the number of how many and a seed value. And so let's start with the range. We know we've done this before, so we can construct a linear domain with a min and a max. And these are going to vary slightly. For our first option, we know that that's from 0 to 360. It works in plan, but in a complete circle. So we can even just set these with expressions. So the first one defaults to 0. The second is set to 1 now. I'm going to set a number to be 360. So this way, my range is from 0 to 360. The number will be the number of random numbers that I want to get. So I can also create a panel so we can see what this looks like. The number is going to be the number of planes. And so let's say 1 is less than 3 is less than 10. And we can use this for all of our 3 random numbers because we want the same number of planes. So I can set this to be plane quantity. And the seed value, I tend to just use 0 is less than 70 is less than 200. We just need to feed it a number. As long as our seed values are different, they will result in a different set of numbers. And I will actually look at that in a second. We'll call this seed 1. And so as we increase, this is good with the panel, we can see we're getting a series of random numbers. All of them fall between 0 and 360. Here they fall between, let's see, 31 and 291. So they meet our criteria. Let's copy this. And for the second range, what we used before was 0 to 90. So this is already set to 0. We can change the other domain to 90. And it'll go from vertical to horizontal as it rotates around. We'll leave the 70 set there. We can see it's actually generating a different set of values because it has a different domain. The cut plane quantity we can reuse, so that's consistent between them. So if we dial this back, we can see it dials all of them back. So it's interesting to know that because there's a different domain, there are a different set of random numbers. So we could almost, because our domains will be different, we could almost use the same seed value for all of them. But we'll do this for now. And let's copy this once more. copy the panel. I could. And our third domain, which is what we set before, we set it to be between 1 and 8. We'll see as we rotate this around, as it gets to 0, 8 is going to be completely outside, and 1 is going to take a large chunk. So we'll start with between 1 and 8, and we'll see if that works. So domain here, we'll change the 0 to 1. We'll change the domain end to be 8. The seed value, we'll change this to seed 3. You'll see there that I'm leaving them all set to 70 now to see what results. And so there's a different set of random numbers within there. But you'll see as we change the seed value, these will change and randomize, and so will these. If the domain was the same, and the seed was the same, and the number of the list was the same, they would be the same numbers. And so this gives us a couple of options here. I can delete the panels just to save some space now. Hopefully you get a sense for that. So our first set, our first domain was from 0 to 360. Let's feed this into our XY angle. We can get rid of that slider. Our second was from 0 to 90. We can feed that into our Z angle and get rid of that parameter. And then our third was a 1 to 8, and we can feed that into our offset. Maybe just a little bit of cleanup here so that we'll move first random number. We can group these. I use my middle mouse and then this option to group. Could maybe even tidy these up a little, bring them in a little tighter. So we can use our groups and even our general location of these to highlight different elements where we want to have maybe a certain type of input. I tend to stack those. So look what's happened to our object on the right. We've got a number of planes cutting through it. I can hide the construction point. We can even increase the number. So here's our cut planes. Let's even increase it to 20. The more we have, the more it's going to become more like a sphere or get smaller and smaller. We can see as we add those, 1, it looks like 8, 10, 12, somewhere in that range. Gives us an object with a number of pieces that are cut off. We start to get a kind of crystallized form. If we change the seed values of any of these, you can see what it's doing is it's changing the numbers in the list and feeding those to the geometry. And so already we've got 3 parameters that are giving us a large number of options. And so this is what we want at an early stage as we're prototyping something. Right? And there's no criteria right now. So in terms of this having massing related to a site or anything like that, we can look at some of those things and we can do that. But for now, we're just looking at what happens when we take 5 planes, or in this case, 12 planes, and cut through an overall form. So that's useful. Let's do 2 simple representational things to this, or operations to this, before we stop this tutorial and we move on to the other one. The first thing that I'd like to do is just go over or add a custom view, a custom display, or a custom preview for the solid. And what we'll do is we'll use the solid difference, right? As I click on this, it turns green. I'll put this into geometry. What we also want to do is you can see that we end up getting both of these. I want to make sure to hide the original object and just to use the custom preview. As I do this, I want to also change the input. So I'll go to parameter, input, color swatch. If I click on the color swatch, I can, let's see, change the hue, which moves that color plane in and out. I can change the saturation. You can see where the point moves across from left to right, or the value up and down. And then the last is an alpha channel if we want to make it transparent. And so let's see, we'll leave the saturation there. We'll turn this up. It's saturated. And then what we have to do is plug this in to material. And so we have that. It's a little strong, so I can turn down the saturation. We could also, you can see as I turn the alpha channel down, it starts to become more and more transparent. That can also be a little confusing as we look at the object, if we can see through it. So here we have our object. Let's do one more thing, and that is that I want to, let's see, under surface and analysis, I want to create a wireframe of our first B-rep as a frame of reference. And so let's do that. Let's bring our center box in as our B-rep, and then we get that object. With lines, you can see how nice the custom display is, or the custom preview is there for surfaces and solids. When it comes to curves, I want to change it slightly in that, let's turn this black. And that looks okay, but if we want to change the line weights a little bit, the trick is to take the geometry and pipe it. And so we'll just use the pipe command. We can bring that curve in and to here. You see that it's very thick, but if we turn the radius down, let's say 0 less than 0.1 less than 1, and set this for our radius, can increase to another decimal place. And now you see we can give it, control that a little bit better. And the same thing, we want to hide these other objects because you can see it's got a little bit of a red tone to it. And that's because these still have objects that are there. So if we only have the custom display on, that turns black. So now we have our original volume as a wireframe, and we have our object on the inside of that. The only thing that I want to do now before we stop at this point is to just talk about a couple of options that you have related to the domain. 0 to 360 is fine. The other one is the 0 to 90. And again, that's assuming it's vertical to horizontal. We could instead set this domain to be, instead of 0, it could be minus 90 to positive 90. It could be minus 60 to positive 60 if we wanted to have the possibility for undercuts within there. And so that results in a very different type of form within that volume, where you're able to get pieces that are cut from the underside of it as well as from the top side of it. And so you can see minus 60 to plus 60, that results in something different. But we could also set it to be 0 to 60. And this will result in no undercuts, more of just a kind of roof form or kind of mountain shape. So those are the couple of options within, and you can play with the domains, you can play with the seed values and see what results. And you'll see that you have options with all of them. And you can play a bit with colors, thicknesses, other types of things as you look at how to represent this. So I think this is a good place to stop for getting that simple overall geometry. So we'll pause here. Let me know if you have any questions, and then we'll pick up part 2 of the tutorial and just look at some of the aspects of breaking out the set of operations and looking at the volume so that we can see that.